In this mini lecture I'm going to show you all how to draw dimethylcyclohexanes. And what we're going to do is we're going to start off with 1, 2, cis, we'll start off with cis 1, 2 dimethylcyclohexane. Now if I want to draw this just regularly, I would do something like this. And if I want to be cis, I would draw it so both of these were sticking down, and I'd use this notation here to show they were both sticking down below the ring. But we're going to do something more than that. We're actually going to draw this as a chair conformation. And remember, when we're drawing a chair conformation, we start off with a lightning bolt. And then we add in our axial bonds. You've seen my previous video for more details about how to do this. So that's the axials. Now we put in the equatorials. Now remember, the axials are all alternating up and down, and the equatorials are also alternating up and down, up and down. The next thing we want to do is put some methyl groups on. Now it doesn't matter where I put my first methyl group. It's going to matter where I put my second though. So what I'm going to do is I'm going to go ahead and put my methyl group here, but I could have put it anywhere. Now I'm going to have to put the second methyl group on. Now I know it has to go on this carbon here, or it could go on this one, but we'll put it on this one here. And it has to be cis, which means if this one's sticking down, which it is, the other one must be sticking down as well. So the second methyl group must go here. Now I know what some of you are saying. You're saying, well, hang on, if that one's equatorial and that one's axial, how can they be cis? Well, cis doesn't matter as far as axial or equatorial goes. All that matters is that one is they're both sticking downwards relative to the ring. This one's sticking down and this one's sticking down. Now we can put our hydrogens on. Now we can draw our other chair conformation. I draw the opposite lightning bolt now. And now I can put in my axial bond. Remember, I always start at the puckered up end. So this axial bond will go there, down, up, down, up, down. Now my equatorials, always sticking in the opposite direction to the axial bonds. Alright, so I'm going to mark this carbon here with a star, and I'll mark this carbon here at the end with a dot. During the course of the interconversion, what's going to happen is this will move down and this one will move up. So this will be the dot carbon and this will be the star carbon. So all the carbons will remain connected to the carbons they were already connected to. Now this methyl group here is sticking downwards and is equatorial. Now what we notice with the interconversions is whatever was axial becomes equatorial, whatever was equatorial becomes axial. So the methyl group is equatorial here, will be axial over here. So it will be this one here. Notice, and we noticed this when we talked about the chair-chair interconversion, is that if you've got a group that's sticking down here in this conformation, it will still be sticking down in this conformation. Even though the equatorial and the axial business have changed, the methyl group will still be sticking down relative to the ring. The other methyl group is sticking down and is currently axial, so we expect that it will be sticking down and be equatorial. Now I'll put my hydrogens on. Now the other question you might be asked here, or will be asked, is, well, which one of these is the lower energy conformation? Well, as I talked about in an earlier mini lecture, I said that anything that has methyl groups in an equatorial position is going to be favored over anything that has methyl groups in an axial position. And we talked about how methyls in equatorials were more stable than methyls in axial positions. And what you've got here is a situation where you've got one axial methyl and one equatorial methyl, and one axial methyl, one equatorial methyl. So there would be no difference in energy for these two conformations. Right, let's do trans 1,2-dimethylcyclohexane. And again, if I drew this regularly, I would put one methyl group down and then draw one up like that, to try and say that one methyl group was pointing below the ring and one was pointing above the ring. Alright, so now I draw my lightning bolts. Doesn't matter which one I start with, I'll start with this one. Now go ahead and put my axial hydrogens in. So I'll start always here at the one that's puckered upwards. Down, up, down, up, and then down. Now I'm going to go ahead and put my equatorial groups in, always in the opposite direction to the axials. Now if I'm going to start here on this one, I guess I'll put a methyl group here. Again, it doesn't matter where you put the methyl group, the first methyl group. It certainly matters where you put the second though. Now this next one has to be trans, which means if this one's sticking down on the next carbon, this methyl would have to be sticking up. And again, the fact that they're both equatorial doesn't mean that they can't be trans. Cis and trans has nothing to do with axial and equatorial. All it's got to do with is what's sticking up and down relative to the plane of the ring. And since this methyl's down and this one's up, this makes it a trans situation. I'm going to put the hydrogens on. Then I will draw the other lightning bolt. And again, I start here at the puckered up one and draw my axial, axial, up, down, up, down. Now my equatorials in the opposite directions to the axials. Now here's my star methyl, my star C, sorry, and my dot C. Here's my dot C, here's my star C. Okay, methyl group sticking downwards, equatorial, now down, axial. Up, equatorial, up, axial. Right, drawing my hydrogens. The other question you'll be asked here is, which is the lower energy conformation? And what I would say is that since this one has two methyls in equatorial positions and this one has two methyls in axial positions, that this one would be the low energy conformation. Remember that large groups like to be equatorial rather than axial.